Hi all, I am Shalu Rose, Assistant Professor in EEE Department from Inverters College of Engineering. Now I am explaining about inverters. First of all, we have to see about IGBT. IGBT is the insulated gate bipolar transistor. It is obtained by combining the properties of BJT and MOSFET. It has three terminals: gate, collector and emitter. Current flows from collector to emitter. Whenever the voltage between the gate and emitter is applied, the IGBT is said to be turned on. When gate emitter voltage is removed, the IGBT is turned off. The gate has full control over the conduction of IGBT. When the gate to emitter voltage is applied, very small current will be flow. Next one is structure of IGBT. Here the base layer is P plus layer. This layer is called collector of IGBT. This P plus injecting layer is heavily doped. It has a doping density of 10 power 19 per centimeter cube. The doping of other layer is similar to that of MOSFET. The N plus layer have 10 power 90 per centimeter cube. This N plus layer is a buffer layer. Next, the N minus drift region is presented. This layer is slightly doped. The doping density of this layer is 10 power 14 per centimeter cube. Then P plus body region has a doping density of 10 power. Next one is punched in IGBT. The N plus buffer layer is not necessary for the operation of IGBT. IGBT which have N plus buffer layer are called punched IGBTs. Such IGBTs have asymmetric voltage blocking capabilities. Punched IGBTs have faster turn-off times. Hence they are used for inverters and chopper circuit. Next one is non-punched IGBT. The IGBTs without N plus buffer layer are called non-punched IGBTs. These IGBTs have symmetric voltage blocking capabilities. These IGBTs are used for rectifier type applications. Next one is operation of IGBT. When VG is turned on, when VG is greater than VGS threshold, then the channel of electron is formed, the gate. These electrons attract holes from P plus layer. Hence holes are injected from P plus layer into N minus drift region. Thus whole electron current starts flowing from collector to emitter. When holes enter P plus body region, they attract more electrons from N plus layer. This action is exactly similar to MOSFET. Next one, now let us see the how P plus layer injecting layer is makes operation different from MOSFET. The MOSFET is formed with the input gate, emitter as source and N minus drift region as drain. The two transistors T1 and T2 are formed. The holes injected by the P plus injecting layer to the N minus drift region. This N minus drift region is base of T1 and collector of T2. The holes in the N minus drift region further go to the P type body region, which is connected to the emitter. The electrons from the N plus regions, that means the emitter, pass through the transistor T2 and further in the N minus drift region. Thus holes and electrons are injected in large amounts in N minus drift region. This reduces the resistance of the N minus drift region. This is called conductivity modulation of N minus drift region. Such conductivity modulation does not exist in the MOSFET. The connection of T1 and T2 is such that large amount of holes electrons are injected in N minus drift region. The action of T1 and T2 is like SCR, which is regenerative. The gate serves as a trigger for T1 to the internally formed MOSFET. When gate is applied, VGS greater than VGS threshold, the internal equivalent MOSFET turns on. This gives the base to drain to T1. Hence T1 start conducting. The collector of T1 is base of T2. Therefore, T2 also turns on. The collector of T2 is the base of T1. Thus the regenerative loop begins and large number of carriers are injected in N minus drift region. This reduces the state of loss of the IGBT just like BJT. This happens due to conductivity modulation of N minus drift region. This is the equivalent circuit of the IGBT. Here PNP and NPN is the transistor. The two transistors will form the IGBT. Next one, when IGBT is turned off, the gate drive is removed. The IGBT should be turned off. When gate is removed, the induced channel will be vanished and the internal MOSFET is turned off. Hence, T1 will turn off if T2 is turned off. T2 will turn off if P-type body region resistance R1 is very small. Under such situation, its base and emitter will be virtually shorted. Hence, T2 turns off. Therefore, T1 will also turn off. Hence, structure of IGBT is organized such that body region resistance is very small. If R1 is very small, then T2 will never conduct, and equivalent circuit of the IGBT is shown below. This is the equivalent circuit of the IGBT. Next one, the latch up in IGBT. Latch up means IGBT remains on condition if gate drive is removed. Causes of latch up: drop across the body region resistance is sufficient to turn off NPN transistor T2. Therefore, PNP transistor T1 is also turned on and regeneration takes place. Under this situation, gate has no control over the current flow. Thus, IGBT remains on condition even if gate drive is removed. To avoid latch-up, effects are made to reduce the body resistance R1. This can be achieved by using special geometrics for the structure of IGBT. The circuit should be designed in such a way that maximum specified current should be HC. Latch-up can also be avoided by increasing the turn-off time and controlling HFE of the PNP transistor. Next one is safe operating area of IGBT. First one is forward biased safe operating area. The forward biased safe operating area is the square of turn-on times less than 1 microsecond. The residual switching times forward biased safe operating area is limited by the maximum junction temperature. Next one is reverse bias safe operating area. The reverse bias safe operating area depends upon the reapplied rate of change of drain source voltage. Observe that reduce the dV ds by dt increased. The prediction of reverse bias safe operating area is necessary to avoid the latch up. Next one is the characteristics of IGBT. First one is static, next one is dynamic. Static means static VA characteristics. Here steady state. First one is sometimes the collector is also called as drain and emitter is also called as the source. The characteristics are plotted for different values of gate to source voltages. When the gate to source voltage is greater than the threshold voltage VGS, then IGBT turns on. The IGBT is off when VGS is less than VGS threshold. The breakdown voltage, drain to source voltage when gate is open circuited. The IGBT is the popular device nowadays. IGBT has simplest drive circuit and it has a earned state losses. Next one is transfer characteristics of IGBT. In transfer characteristics, the plot of the collector current with respect to the gate emitter voltage. In this characteristics, the collector current rises heavily when VG is greater than VGET. The VGET is gate emitter threshold voltage. Observe that once the IGBT goes in the conduction mode, its collector current rises almost linearly with respect to the gate emitter voltage. Next one is the switching characteristics of the IGBT. The gate to source voltage is normally negative. This voltage is made positive to turn on the IGBT. When VGS greater than VGS threshold, the collector current starts increasing. Turn on delay TD is the delay when gate drive is applied and IC starts increasing. When IC increases to its full value, collector emitter voltage starts falling. TRI is the rise time in the collector and TFE is the fall time voltage. The turn on time of the IGBT is T on is equal to T. The turn off of the IGBT is initiated by reducing the gate voltage. When gate voltages fall to value of the equal to VGS1 and VC starts rising. VC means voltage between collector and emitter. VGS1 is the voltage where IGBTs comes out of saturation. Turn off delayed TD off is the delayed time when gate voltage is reduced and VC starts increasing. When VC reaches to supply voltage, IC means collector current start reducing. IC reduces fast till VGS reaches to VGS threshold. This fast delay in the IC basically due to the internal MOSFET. Then when VGS goes to 0 and becomes negative, but IC keeps on flowing for some time, this is internal BJT current. This currents flow due to the stored carriers in the drift region. And start off time of the IGBT is higher than MOSFET. The turn off time of IGBT will be turn off is equal to TD plus TRV, TF1 plus TF2. TRV is the voltage rise time. TFI1 is the MOSFET current fall time. TFI12 is the BJT current fall time. Okay. Next one is inverters. The inverters is a device or circuitry that changes direct current into alternating current. The input voltage, output voltage, and frequency and overall power handling depend on the design of specific device or circuitry. The inverter does not produce any power. The power is provided by the DC source. It converts the DC power to AC power of desired output voltage and frequency is called the inverter. The output voltage can be fixed or variable at the fixed or variable frequency. The inverter gain is the ratio of the AC output voltage to the DC input voltage. There are two types of inverters, single phase inverter and three phase inverters. The single phase in single phase it also divided into two types, half bridge inverter and full bridge inverter. In single phase half bridge inverter, the inverter is a type of single phase bridge inverter. It is a voltage source inverter. Voltage source inverter means that the input power of the inverter is the DC voltage source. The output of the single phase inverter circuit is a single phase output. Working principle: the inverter circuit consists of two thyristors T1 and T2 and two diodes D1 and D2 and 3 wire DC supply Vs by 2. During the time of 0 to T by 2, the thyristor or IGBT any switch will be conducting the gate signal IG1. The voltage across the resistive load is Vs by 2 due to the upper voltage source Vs2. At T is equal to 2, the thyristor is turned off by force combination and T2 is turned on. During the time of the T by 2 to T, thyristor T2 conducts the voltage across the resistive load is minus Vs by 2 due to the lower voltage source Vs by 2. Thus the load voltage V0 is an alternative voltage waveform of amplitude Vs by 2 and frequency 1 by T Hz. The output frequency can be changed by the changing T. The resistive load is the load voltage of the V0 and load current is I0 are in phase with each other. For inductive load, the load current I0 will not be in phase with load voltage V0. The diodes D1 and D2 which are connected and anti-parallel with the thyristors carries the current when the thyristors are turned off. These diodes D1 and D2 are called the feedback diodes. Next one is single phase full bridge inverter. In single phase full bridge inverter is basically voltage source inverter. Unlike single phase half bridge inverter, this inverter does not require 3-wire DC supply. Rather, 2-wire DC supply will be sufficient for requirement. The output frequency can be controlled by controlling the turn off and turn off time of the thyristor IGBT. Then it is a circuit diagram of the single phase full bridge inverter. The thyristor T1 and T2 should be turned on simultaneously at frequency f is equal to T by 2, 1 by T. And thyristor T3 and T2 should be turned on 180 degree out of phase with the T1 and T2. Frequently, the output voltage can be controlled by varying the time period T. When thyristor T1 and T2 conduct, load voltage is positive, that is Vs. When thyristor T2 and T3 and T4 conduct, the load voltage is negative, that is minus Vs. The load voltage waveform is rectangular and is not affected by the nature of the load. The amplitude of output voltage and output power single phase full bridge inverter is doubled when compared to single phase half bridge inverter. During inverter operation, the two resistors same branch, that is T1 and T4. Similarly, T2 and T3 should not conduct simultaneously, which is lead to the short circuit of the source. The load voltage V0 and load current I0 will be phased with each other for R load. Next one is single phase full bridge inverter with the RL load. Let us consider the single phase full bridge inverter with the inductive load. Before T is equal to 0, there is a T3 and T4 are conducting and load current I0 is negative. At T is equal to 0, T3 and T4 are turned off and load current is I0 should be positive. But due to inductive load, the load current I0 cannot change its direction immediately. As a result, diode D1 and D2 start conducting after T is equal to 0. Now the load current I0 flows against the supply voltage Vs. Even though T1 and T2 are gated at T is equal to 0, they will not turn on because T1 and T2 are reverse biased by voltage drops across diodes D1 and D2. When the current through D1 and D2 falls to 0, T1 and T2 become forward biased by voltage Vs. Thus, T1 and T2 are turned on for the period of T2 by 2. Now the load current I0 is positive. At T equal to T by 2, T1 and T2 are turned off by forced computation. The load current I0 cannot reverse its direction immediately. So diodes D3 and D4 start conducting after T is equal to T by 2. Though T3 and T4 are gated at T is equal to T by 2, they will not turn on because T3 and T4 are reverse biased by voltage drops across diode D3 and D4. When current in diodes D3 and D4 falls to 0, T3 and T4 are turned on. Now the load current I0 is negative. This process is repeated. Next one, the three-phase inverter. Three-phase inverters are used to supply the three-phase loads. These three-phase loads can also be supplied by the three-phase separate single-phase inverters. The input to the three-phase bridge inverter is DC supply, which is taken from the battery or from the rectifier. The three-phase inverter is also called as the six-step bridge inverter. The three-phase bridge inverter power circuit using 6 IGBT and 6 diodes. The three-phase load may be either star connector or delta connector. The three-phase there are two modes of operation: 180 conduction mode and 120 conduction mode. First one is the 180 conduction mode. In this scheme, this is called 180 conduction mode of operation. The maximum of three-phase IGBT conduct at any instant, and each ACRs conduct for pi radians in every cycle of the output. ACR pair in each leg is, that is T1, T4, T3, T6 and T5, T2 are turned on with a time interval 180. It means that IGBT T1 conduct for 180 degree and IGBT T4 for the next 180 degree of the cycle. IGBT in the upper group, that is T1, T3, T5 conduct at an interval of 120 degree. It means that if IGBT T1 is 500 degree, then T3 must be triggered at 120 degree and T5 at 240 degree. Same is true for the lower group of IGBTs. On the basis of this firing scheme, table is prepared. Next one is 120 conduction mode. In this conduction mode, each IGBT conduct for 120 degree. At any instant of time, only 2 IGBT remains on. Here also gate pulse indicates the conduction period of each IGBTs. Here 6 computation per cycle is required. Like 180 conduction mode, 120 mode inverter also requires 6 steps, each of 60 degree of duration for completing one cycle of the output AC voltage. Next one, the THD calculation. The THD is the total harmonic distraction. It's a square root of sum of the squares of harmonic voltage divided by the fundamental voltage, which must be under 5% of the acceptable for the current wave form. THD is equal to root of V2 V2 square plus V3 square plus V4 up to Vn divided by V1. V1 means fundamental voltage. Okay. Next one is efficiency calculation. The efficiency of the inverter can be found by dividing the output power to the input power. Efficiency is equal to P out by Pin, and it can also perform as percentage. Efficiency is equal to P out divided by Pn into 100%. Next one is voltage source inverter. In voltage source inverter, the input voltage is maintained constant, and amplitude of the output voltage does not depend upon the load. However, the waveform of the load current as well as the magnitude depend upon the load impedance. Next one is current source inverter. In current source inverter, the input current is constant and adjustable. The amplitude of the output current from CSI, that means current source inverter, is depend upon the load. In the current source inverter, the current for inverter, the current from the DC source is maintained at an effectively constant level, irrespective of load or inverter conditions. This is achieved by inserting a large inductance in series with the DC supply to enable changes of inverter voltage to be accumulated at low values of dI by dt. Next one is the characteristics of a good inverter. Its output voltage waveform should be sinusoidal. The gain should be high. Its output voltage and frequency should be controllable in the desired voltage. The power required by its controlling circuit should be minimum. Next one is its overall cost must be minimum. Its working life must be long. The semiconductor device used in the inverter should be minimum switching and conducting losses. Next one is the voltage control of inverter. The voltage control of inverter consists of two types. First one is pulse width modulation control. Next one is phase vector modulation. First one is the pulse width modulation. It consists of four types: single phase, multiple phase, sinusoidal, modulate sinusoidal, and phase displacement control. The output voltage of the inverter may be not remain constant value due to the variations in the output voltage and the voltage drop in the inverter. At the same time, some special applications require variation of voltage and frequency. Therefore, output voltage of inverters can be controlled to the desired level. Advantage of the voltage control: as the inverter output voltage is controlled through the adjustment of the DC input voltage to the inverter, output voltage waveform and its harmonic contents are not affected appreciably. If the DC input of the inverter is varied to compensate for the source voltage fluctuations, the inverter can be designed for the very limited voltage range. Such an inverter is the most efficient both in terms of power losses and component utilizations. Next one is pulse width modulation control. In this method, a fixed DC voltage is applied to the inverter and a controlled AC voltage is obtained by adjusting the on and off periods of the inverter power circuit devices. The PWM controls has following advantages. The output voltage can be obtained without any additional components. The lower order harmonics can be eliminated or minimized along with its output voltage control. The filter equipments are minimized as higher order harmonics can be filtered easily. Types of PWM techniques. First one is single phase PWM pulse width modulation. Next one is multiple phase width modulation, sinusoidal pulse width modulation, modified sinusoidal pulse width modulation. Next one is phase displacement control. First one is single pulse modulation. This modulation gives quasi square wave output. Observe that there are single pulse of output voltage during each half cycle. The width of the pulse is 2D. RMS values of output voltage can be controlled by the varying the pulse width. Next one is generation of single pulse modulation. The ratio of triangular signal amplitude and square wave signal amplitude is called the modulation index. The width of the pulse can be changed by varying the modulation index. When m is equal to 1, square wave in output is obtained. Next one is multiple pulse width modulation. In this method, the pulse width modulation, the harmonic content can be reduced using the several pulses of each half cycle of output voltage. By comparing the reference signal with the triangle carrier wave, the gating signal can be generated for turn on and turn off the IGBT. The carrier frequency Fc determines the number of pulses per half cycle M, whereas the frequency of reference signal sets the output frequency F0. The modulation induction controls the output voltage. This type of modulation is also called as the symmetrical pulse width modulation. The number of pulses Np per half cycle is found at the expression Np is equal to Mf by 2. Next one is sinusoidal pulse width modulation. In this method of modulation, several pulses per half cycle will be used in case of multiple pulse width modulation. Instead of maintaining the width of all pulses the same as the in case of multiple pulse modulation, the width of each pulse is varied proportional to the amplitude of the sine wave evaluated at the control of the same pulses. By comparing a sinusoidal reference signal with the triangle carrier wave of this frequency Fc, the gating signals are generated. The frequency of reference signal Fr determines the inverter output frequency F0 and its peak amplitude Vr control the modulation index M1 and turns the RMS output voltage VL. The number of pulses per half cycle depends on the carrier frequency. Within the constraint, the two IGBTs of the same arm cannot conduct at the same time. The same gating signal can be generated using the unidirectional triangular carrier wave. By varying the modulation index M1, the RMS output voltage can be varied. The harmonic analysis of the output modulator voltage wave reveals the space width modulation has the following important features. For modulation index less than 1, the largest harmonic amplitude in the output voltage can be associated with the harmonics of order. Next one is the modified sine pulse width modulation. Here we can compare the sine wave and triangular wave. Sine wave is a reference signal and triangular wave is the carrier signal. In this method, the carrier signal is applied during the first and last 60 intervals of the half cycle. 0 degree, 60 degree and 120 degree to 180 degree carrier signal is presented and 60 to 120 degree the carrier signal is not presented. Comparing these two signals, we can get the output pulses. This output pulse is fed to the inverter circuit. Next one is advantages. The fundamental component is increased. Its harmonic characters are improved. It's reduced the number of switching of the power consumption devices. The switching losses are also reduced. Next one is space vector modulation. The space vector modulation considers inverter as a single unit rather than the separate phases. The required output waveforms are generated by driving the inverter in 8 unique states. Digital circuits are used to implement the SPM technique. The control is such as the PWM load line voltage are in the average equal to the given reference load line voltages. The stages of the switches are properly selected in each sampling period. The period of the stages are selected such that the output waveforms have quarter cycle symmetric. The states of the switches and their time periods are accomplished with the help of the space vector transformation. The advantage is more efficient and precise harmonic and voltage control. All the three phases are controlled as the single unit. Disadvantages: the control is complex and difficult to implement. Next one is the harmonic control of the inverters. The power electronics equipment such as rectifiers, inverters, choppers, and the switching devices and their operations produce the current and voltage harmonics into the system from they are working. This harmonic affect the operation of other equipments connected to this same system through the conduction or by radio interference. The harmonic present in the inverter system lead to the following disadvantages. Harmonic currents will be lead to excessive heating in the induction motors connected with the thyristor system. This will reduce the load carrying capacity of the motor. If the control of regulating circuits are not properly shielded, harmonics from power side can affect the operation and malfunctioning can result. On critical loads, torques pulsating produced by the harmonic current will be harmful. Harmonic currents causes the losses in the AC and AC systems can even sometimes produce the resonance in the system. Under the resonance conditions, metering and instrumentation may also be affected because of the distraction, etc. This effect can be minimized by reducing this harmonic content. There are various methods available to reduce the harmonic content. The reduction of the harmonic content or the improvement in the wave shape can be done by following methods. First one is single pulse width modulation. Next one is transformer connection. Multiple commutation in each half cycle stepped wave inverters. First one is the harmonic reduction by single phase pulse width modulation. In this case, single pulse modulation, the width of the pulse is adjusted to reduce the harmonic. In general, the RMS value of the amplitude of the harmonics will be given by the 2 root 2 Vs by n pi sin n pi by 2. Next one is the transformer connection. To get the voltage, then to get the output with a reduced harmonic content, the output voltage from two or more inverters can be combined by means of the transformers. The output waveforms from the inverter must be similar but phase shifted from each other. In this method, it is possible to eliminate third order harmonics. Along with the third harmonics, the multiple of third harmonics such as 9, 12 are also eliminated. The main drawback of this method is harmonic reduction is need for the more number of inverters and transformers for a similar rating. Next one is harmonic reduction by the multiple commutation of in each cycle. This method is explained with respect to the single phase inverters. Normally there is one commutation per cycle is end of the each half cycle. This produces square wave output. Instead of having commutation at the end of half cycle, some more commutations can be created in the half cycle. By properly selecting the values of the delay angle alpha 1 and alpha 2, any two unwanted load or harmonics can be eliminated from the waveform. With this method of harmonic reduction, inverter is rated by 16.1%. Another disadvantage of this method is that there are additional 4 computations per cycle, and this leads to more switching losses which decrease the efficiency of the operation. Next one is harmonic reduction by using a stepped wave inverter. This method may be called as wave stepping, in which pulses of different widths and heights are added to produce a resultant stepped wave with reduced harmonic content. Two step wave inverters swept from the common DC input voltage. These inverters are connected to a common load through transformers having turns ratio 1:3 and 1:1 respectively. The inverter 1 is so operated that output voltage is VLN. The output voltage level is either 0 or positive during the first half cycle. During second half cycle, the output voltage would be either 0 or negative. This type of modulation in which the output voltage has only two levels of during the half cycle is called as two-level modulations. The inverter 2 is so operated that its output voltage is VL2. It is observed from VL2 waveform that is level of output voltage is positive, 0 negative during the first half cycle. Therefore, inverter 2 is operated with a three-level modulation. The load waveform shows that the amplitude of the output voltage is 4 Vs and waveform has 4 steps. Harmonics whose amplitude should be depend upon the values of P1, P2, P3, P4 and amplitude of VL. By proper choice of these parameters, third, fifth and seventh harmonics can be decreased considerably and the fundamental component optimized. It is noted that the three-level modulation of inverter 2 helps achieving the required of the stepping of the resultant output voltage waveform. Next one is the current source inverter. In a current source inverter or current fed inverter, the current in the current from the source is maintained at the effectively constant level irrespective of the load or inverter conditions. This is achieved by inserting a large inductance in series with a DC supply to enable changes of inverter voltage to be accumulated at low value of dI by dt. Now we have to see about the single phase capacitor combinated current source inverter with resistive load. Capacitor C is parallel with the load is used for storing the charge for accommodating the IGBTs T1, T2, T3, T4 from the power circuits. These IGBTs are triggered in pairs T1 and T2 together by getting signals IG1 and IG2 and T3, T4 by IG3, IG4 before T is equal to 0. The capacitor voltage Vc is equal to 1, that is capacitor has right plate positive and left plate negative. At T is equal to 0, IGBT by N T1 and T2 are triggered, and when T1 and T2 become turned on, capacitor applies reverse voltage across the previously containing IGBTs T3 and T2, T4 and can turn them off. The source current I1 now flows through the IGBTs T1 parallel combination of R and C and to IGBTs T2. From 0 to T2, IT1 is equal to IT2 equal to I. Output current IAC minus I. Capacitor voltage Vc changes from minus V1 to plus V1 through the changing of the C current IC. Hence, load voltage VL is equal to Vc. Thus, the waveform IL is equal to VL by R, Vc by R has the same nature as the Vc. Next one is the single phase auto sequential combinator inverter. Here the four combinating circuit components are included. The two capacitors store the energy necessary for commutation. The four series diodes are effectively prevent the capacitors from the discharging through the load in the interval between inverter commutations. IGBT pair T1 and T2 and T3, T4 are alternately switched to obtain a nearly square wave load current. As usual, the triggering frequency of the IGBTs determines the output frequency. The circuit behavior during the commutation interval is highly load dependent. The operation of this inverter circuit can be divided into four operating modes. Mode 1. In this mode between commutations, the constant source current I1 is flowing in the load and hence the load voltage is R1. IGBTs T1 and T2 are conducting and the current I is established in the circuit consisting of T1 and the load T2 and T2. The capacitance C1 and C2 are changed to the voltage Vc is equal to plus VL from the previous half cycle. Mode 2 operation. When IGBT T3 and T4 are gated on, the capacitors C1 and C2 apply a reverse bias to IGBTs T1 and T2 respectively, causing them to turn off. However, the load current I continues to flow in the same directions as before through the T3, C, T1, the load D2, C2 and T4. The capacitors are in series with the load and are discharged by the constant current I. When the capacitor voltages have fallen from VL to R1, diodes D4 and D3 conduct and mode 2 is terminated. Mode 3. IGBTs T3 and T4 and all four diodes are now conducting so that the load is effectively in parallel with the both commutating capacitors. This RLC circuit undergoes a transient response during which the load current falls to 0 and reverse. When a load current attains a value minus I, the diodes D1 and D2 become reverse biased. This terminates mode 3 and completes the commutation process. Mode 4. For the next half cycle, the source current I is flowing through the T3, D3 and the load D4 and T4. The capacitor voltage is now minus VL and the capacitor hold this voltage until next computation. The DC current source delivers a unidirectional current I to the inverter, and whenever the inverter feeds the reactive or regenerative load, the DC supply current cannot reverse as it is because the voltage source inverter. However, the feedback diodes of ES1 have been removed, flowing the DC link voltage to change polarity and permitting a return of energy to the DC link by reversal of the DC link voltage rather than the reversal of DC link current. When IGBTs T3 and T4 are gated to integrate the mode 2, the inverter input voltage Vs goes negative and remains negative throughout this interval. Hence, input power Vs1 is also negative, indicating the power is being returned to the DC current source. It is the voltage source inverter. Next, the catches of good inverter output voltage waveform should be sinusoidal. Its gain should be high. The output voltage and frequency should be controllable to the desired voltage. The power required by the controlling circuit should be minimum. Its overall cost must be minimum. Its working life must be long. The semiconductor device, usually inverter, should be minimum switching and connecting losses. Here in this inverter, in this unit, we use the IGBT as a switch. Okay, that's why we studied in the previous section. This is already we have to study harmonic control. Actually, one topic is okay. This operation. Okay, this is the output waveform of three-phase inverter. Okay, in single phase means only one sine wave will be presented. In three-phase means three sine wave will be presented. Okay, so it have the 90-degree phase shift, phase 1, phase 2, phase 3. Three phase of the voltage will be presented. Here it is the 120 mode of the operation. Actually, next one is THD calculation. THD means total harmonic distraction. The blue line is the fundamental sine wave component. The square wave. Next, the green line is the third harmonic. The orange line is the fifth harmonic. Actually, in THD calculation, the sine wave will be compared to square wave. Then we found the output. Harmonic means first order, second order, etc. will be presented in the circuit. Actually, it is the square root of the harmonic voltage divided by the fundamental voltage, which moves under 5% of the excitable of the current waveform. THC is equal to V2 square. V2 means second harmonic, V3 means third harmonic, V4 means fifth harmonic, Vn means nth harmonic, divided by V1. Next one is the efficiency. Efficiency means out by n. Here the power efficiency means power out by power n. The efficiency of the inverter can be found by dividing the output power to the input power. Efficiency is equal to P out divided by Pn, and it can also performed as a percentage. Efficiency is equal to P out divided by Pn into 100%. Voltage source inverter. Here voltage will be controlled. Current source inverter. His harmonic voltage controlled. Two types of voltage controlled. Okay. Next one is harmonic control of inverters. This is the inverter circuit.
It is the switch of the inverter. Okay. Thank you.